Still hearing me? Da 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 da.
We're still rolling. So.
No biggie. Oh no, I just did that in front of the camera. Alex, please don't put that in the video. I was just singing da 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 da, some nonsense. Dude, just don't.
Da 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 da.
Knowing you damn well will. But anyways. Alright, at least it's entertainment for the masses. Welcome to the first episode of CSEC Physics with me, Marvin Lee, for the year 2021. The first episode we're recording, I'm not sure if this is the first one you're gonna see, but having taken a break for the holidays, today we will take a break from regular teaching. The aim of today's lesson is to do some revision. Now, revision is key, vital, important, and very necessary. A lot of work has been done. Let's be honest, a lot has been done, and we've tried our best to get a lot of content across in each episode. So just to aid the process of revision and to enhance your memories, today we will go over what we have done. Now, we're not going to go over everything. We have to partition it into 2 revision episodes. This is the first. The other revision episode will do everything else that we don't cover today. So in 2 episodes, we should be able to revise mechanics in its entirety. Now, we have to begin with the fundamental quantities and units. In that lesson, we looked at the importance of fundamental quantities and units, and what was said was really simple. They're necessary for communication and for understanding. Now, there are 7 fundamental quantities, and at this level you only actually make use of 5. I shouldn't say you only should know. You only use 5. Now, the 5 we use are mass, length, time, amount of current, and temperature. Mass is a measure of the amount of substance an object contains and is measured in kilograms. Length is measured in meters. Time is measured in seconds. Amount of current is measured in amperes, and temperature is measured in Kelvin. And I beg you, please don't say degrees Kelvin. It's just plain old Kelvin. So, fundamental quantities is off our list. The next thing we have to quickly go over is mass versus weight. What are the differences? Now, mass, like I said earlier, is the amount of substance an object contains. If an object is 600 grams, it has 600 grams of substance. Weight is not mass. Mass is not weight. They are related, but they are not the same. Mass is the amount of substance an object contains measured in kilograms, and weight is the force exerted by gravity on mass. Weight is a force exerted by gravity on mass, and as a result of this, weight acts downwards. Okay, that is why objects that are heavier, which basically means they have more mass, they are harder to move and lift, because you're essentially moving the object against the downward force of gravity. Mass is measured in kilograms, weight is measured in newtons. Volume and density. There's that age-old definition. You learn it in primary school. What is matter? Matter is anything that has mass and takes up space. We know that. Now, the taking up space part is what volume addresses. Volume is the amount of space an object occupies. Okay? Now, 2-dimensional objects, for example, sheets of paper, they do have volume if you kind of fold them, I guess, but they don't have a lot of volume because of their thin nature. Yes, there is volume, but because they're essentially 2-dimensional, they don't have volume. They occupy a plane, a flat 2-dimensional surface. Solid objects like yourself, your phone, tablet, house, these objects, because of the fact that they are 3-dimensional, they have height, length, and width. They occupy 3-dimensional space, therefore they have volume. Now, volume is measured in meters cubed, centimeters cubed, millimeters cubed. It depends on the size of the object. The larger the object, the larger the unit used. The smaller the object, the smaller the unit used. So let's say if you have an eraser, you will not easily be able to, or you shouldn't rather, express the volume of a small eraser in terms of meters cubed. It would not be right. However, if you have like a refrigerator or a cupboard or a massive storage unit, meters cubed, yeah, that works. Now density. Density is the, I shouldn't say combination of, but density is affected by both mass and volume. The density of an object is mass contained in unit volume. So, another formula, density represented by the Greek letter rho is equal to m over v. Common m, common v, or lowercase m over lowercase v, however you say it. Density is mass over volume. And again, for small objects, density is expressed in grams per cm cubed, and for very large objects, it's expressed in kilograms per meter cubed. So, volume, amount of substance, an object, sorry, the amount of space an object occupies, density is the mass per unit volume. Then there is relative density. Relative density is simply the density of a substance divided by the density of water. It was once called specific gravity, but we don't call it that anymore. Now, relative density is important because it determines whether an object will float or sink. If the relative density of an object is greater than 1, it will sink. If it's less than 1, it will float. Now, density of substance divided by density of water. That is the formula for relative density. And finally, before I take my first break, forces. Now, I put the word forces there, but we should start off with what a force is. A force is any action which can change the size, shape, or basically the motion or behavior of an object. Size, shape, motion. The three things that can be influenced by the action of a force. Now, forces can compress objects, changing their size. You can deform objects, changing their shape. And force can put an object into motion, cause an object to stop moving, and even cause an object to change its direction of motion. Now, the unit of force is the Newton, named after, of course, Sir Isaac Newton. I like the unit. And there are 4 types of forces we have to look at this level 4. We have to look at magnetic forces. These are forces that exist between any 2 magnetic poles. Nuclear forces. These are found within the nucleus of the atom and are responsible for holding it together. You have gravitational forces, the forces that act between any 2 masses. Now, gravitational forces act between literally any 2 masses. As long as there's mass, there is gravitation. You might be thinking, but why am I not attracting things? The reason you're not able to move anything with your mass, I mean, please don't stand and try to, move anything. It won't work. Why it doesn't work is really simple. The Earth's gravitational force is so strong that your gravitational force will not affect an object the Earth's gravity acts on. All right, it's kind of like 2 people pulling on one object in opposite directions. You're the small person, and the Hulk is essentially the other person. Your gravitational pull versus the Earth's gravitational pull, it's not a fair fight. The Earth's gravitational pull will win. This is why, even though you have a gravitational pull, you're not attracting anything. And finally, electric forces, and these exist between any 2 charged particles or objects. Now, it might not seem an impressive thing, but electrical forces are fairly strong and, more importantly, fairly dangerous. So, we went over very, very briefly fundamental quantities in units, the 5 of them: mass, length, time, temperature, and amount of current. We went over mass, which is the amount of substance an object contains; weight, which is the effect gravity has on mass, or the force exerted by gravity on mass. We went over volume, the 3-dimensional space occupied by a solid object; density, mass over volume; relative density, which is density of substance divided by density of water; and finally, forces, or force, if you want to put it that way. Force is the or force is the action which can change the size, shape, or motion of an object. And the four forces are magnetic, gravitational, nuclear, and electric. In our next section, we shall do some more revision. Welcome back. We're continuing with our revision today. And having looked at forces, we have to look at the things forces do. Now, I don't want to say effects of forces, that sounds so boring. Things forces do, much cooler. The first thing we have to look at is deformation. Now, deformation is caused by the force changing the physical dimensions of the shape, the object, whatever you want to call it. And there are two types of deformation. There's plastic, which is permanent, which we do not examine, and then there is elastic, which we mercifully do examine. Now, elastic deformation is temporary deformation. It doesn't remain. It happens, but then the object goes back to how it was previously or originally. For example, if you squeeze one of those rubber balls, if you squeeze it and you release it, it's going to go back to how it was. It's not that the object was not deformed. It's just that the deformation is not permanent. So, an elastic object tends to go back to how it was once the force that deformed it has been removed. All right, that's the concept of elasticity. You stretch or you compress, it goes back to how it was. Now, the behavior of all elastic objects is governed by Hooke's law. Hooke's law. Now, Hooke simply said that the force which is responsible for this deformation is proportional to the extension obtained. All right, in other words, if you apply a force to stretch an object, the force is proportional to the extension you obtain. Now, this doesn't happen all the time or endlessly. It happens up to a point called the elastic limit. Now, the elastic limit, as the name suggests, mind you, is the limit of elastic behavior. I mean, past the elastic limit, the object doesn't behave in an elastic manner. That elastic behavior is no more. So Hooke's law governs the behavior of elastic objects and says force is proportional to extension when you're stretching the object. Up to, of course, the elastic limit. Now, the second effect of a force for this syllabus is the turning effect or moment of a force. Now, when a force is applied to an object that is pivoted and can freely rotate about said pivot, you have rotation. For example, doors, pair of scissors, a can opener. These are all cases where you have a pivot and you have rotation about said pivot by the application of a force. And of course, the crowbar is another example of a tool that uses or utilizes the principle of moments and essentially the turning effect or moment of a force. Now, I mentioned principle of moments, and let me explain what that is. Now, if you push a door, you're exerting a force on that door. The door rotates about its hinges and closes. There are cases where there's more than one force acting on an object that can rotate about a pivot. In those cases, we apply the principle of moments. The principle of moments simply states that for a system in equilibrium, the sum of clockwise moments is equal to the sum of anti-clockwise moments about the same point or about the same pivot. That simply means if you have an object and there are multiple forces acting on the object, and this object is balanced or in equilibrium, or it's not rotating, simply put, the total clockwise moment is equal to the total anti-clockwise moment. Now, the formula is fairly simple and straightforward. You just apply it based on the situation you're in. But when it comes to moment, you might be like, sir, you're using the word moment, but you didn't explain what a moment is. Well, essentially, the moment of force or the magnitude of the moment of force rather, is calculated by multiplying the force or the size of the force by the perpendicular distance from the pivot. All right. Now, if the perpendicular distance from the pivot, by that I simply mean how far the force is from the pivot multiplied by the magnitude of the force. That's very, very, very simple. All right, nothing complicated. The symbol for moment of force is capital T, the symbol for force is capital F, and the symbol for distance is common or lowercase d. So T is equal to F times d. T, turning effect or moment of force, is equal to F by d. And when it comes to the principle of moments, you simply find the moment each force will produce, add the moments that cause clockwise rotation, and equate it to the moments that cause anti-clockwise rotation. Presto, you're done. So, things forces do, two of them: deformation, changing of physical dimensions by the application of force, and two, turning effect, rotation about a fixed point by the application of a force. Now, moving on, straight line motion. The obvious must be stated, it's on a straight line. I know, it's on a straight line. By the way, a straight line should be straight. I'm saying this because every time I teach and try drawing a straight line free-handed, it's not a straight line. But I tell my students to imagine. They know what I'm talking about. On a straight line, when we're looking at motion rather on a straight line, uniform motion on a straight line, we have 5 terms we need to be familiar with. First of all, there's distance. Now, distance is the length of a journey, or how far you have traveled. Displacement is distance, but in a set, specific, or particular direction. So instead of saying I just walked 3 meters, that's just distance. Displacement would be specific and say I walked 3 meters east. The difference is not in how far you've moved, but in your direction being stated. We prefer to use displacement over distance for the simple reason displacement gives us more information. Distance is just 3 meters. Sorry, distance is just 3 meters. Displacement is 3 meters east. Then from these 2 terms, we have 2 more terms developed. We have speed and velocity. Now, distance is what gives us speed, or the rate of change of distance rather is what gives us speed. Speed is the change in distance over time taken. Change in distance over time taken. Velocity is the change in displacement over time taken. Again, if we choose to use displacement over distance, we will choose to use velocity over speed. Okay? Because again, direction is given, implied, and known once we know displacement. So if we say 3 meters east as our displacement, velocity would be 1.5 meters per second east, because we traveled at that rate in that direction. Again, distance, just how far you traveled. Displacement, how far you've traveled in a given direction. Speed, the change in distance over time taken, or the rate of change of distance. Velocity, is the change in displacement over time, or the rate of change of displacement. We choose displacement, we choose velocity, because they give us more information. And finally, the king of them all is acceleration. Acceleration is the change in velocity over time, or the time this change takes. Change in velocity over time taken. And as a formula, cheat sheet, A is equal to V minus U divided by T. V is initial velocity. U, why did I say V is initial velocity? V is final velocity, sorry. U is initial velocity and T is time. A is equal to V minus U upon T. Again, A, acceleration. V, final velocity. U, initial or starting velocity, and T, time. Velocity has units of meters per second, ms to the -1, or m/s, however you choose to write it. Acceleration has units of meters per second squared, ms to the -2, or m/s squared. Please note your units, please note your formulae, please note these differences. So I will take a break now, grab a drink of water, and I will come back for us to look at Aristotle, Newton's 3 laws, and good old momentum. So, see you soon. Welcome back, having had my sip of water and a chance to rest my voice for a few. Time to look at our last 3 main topics for this revision lesson. Now, for fun, I want you to actually, like, when you go through this lesson, check to see how many times I said the wrong thing. Like, you know, mixed up my terms. Ever so often it happens. You could count my mistakes and tell me. I mean, I'm probably guilty of making a few more than I should have, but trying to be concise is a bit difficult at times. Now, enough of me giving you extra work. Aristotle. Now, Aristotle is credited with giving us one of the first theories of motion. Aristotle said that the velocity with which an object moves is directly proportional to the force applied to move it. He was somewhat right because his theory applied to horse carts. Now, if you understand a horse cart or any horse-drawn or animal-drawn vehicle, you'd realize that the faster and stronger the animal pulling, the faster the pulled object or the cart can move. Now, if you have one horse, that one horse is going to lose to a carriage or cart drawn by 4 horses. Because again, more horses, more horsepower. But his theory did actually give us a starting point. It might not have been the most sound or thorough theory, but it gave us a starting point, and that is totally accepted and appreciated. Because again, sometimes you don't need to be perfect, you just need to start. I know, big life lesson, but velocity proportional to force made sense, but it didn't cover all scenarios, so it was eventually done away with. And it was done away with by Newton's 3 laws, Newton's 3 laws of motion. Now, the flaw in Aristotle's theory is that he didn't take into consideration what would happen if the force became 0. Because if velocity is proportional to force, what happens when force is no longer there? Does the object instantaneously stop? Does it explode? Does it turn into something else? He didn't state. So his theory, though useful, was eventually replaced and totally outdone by Newton's works. Now, good old Newton came up with 3 laws of motion, and I will start with the 3rd law because it's the easiest and the one people tend to quote, like I said previously, like it comes from the Bible. It does not come from the Bible. It's not found in any religious book. The 3rd law, created by Newton, simply states to every action there's an equal but opposite reaction. To every action there is an equal but opposite reaction, meaning if you push on an object, the object will push back. Simply put, forces act in pairs. Forces act in pairs. That's the 3rd law. The 2nd law of motion, yes, I'm working 3, 2, 1. The 2nd law of motion simply states the relationship between force, mass, and acceleration. Okay, force, mass, and acceleration. The acceleration produced by an applied force is in the direction of the applied force, proportional to the magnitude of the applied force, and inversely proportional to the mass of the object. Simply put, how fast you change motion depends on the size of force you apply. If you're in a car and you want to truly accelerate, you don't ease onto the gas or the accelerator. You kind of floor it, the car shoots off. If the car is traveling at a decent clip and you're trying to slow down in a hurry, you don't ease onto the brake. You, as Guyanese say, mash brakes, and the car comes to a screeching halt. The change in acceleration is proportional to the change in force. Okay? Now, the 2nd law gives us that good old equation, hint, hint, equation, cheat sheet time. F is equal to m times a force is equal to mass times acceleration. Force is equal to mass times acceleration. Now, this equation also gives us the concept of impulse. Impulse is simply the byproduct of force and the time for which the force acts. And if we have a large force, I shouldn't even say this, but if we have a large force acting for a large amount of time, we have a massive change in the object's momentum. If, however, we have a small force acting for a small period of time, we have a small change in momentum. Impulse is the product of the force applied to an object and the time for which that force acts. So again, cheat sheet, equation time, Ft is equal to change in momentum. am I defining momentum without explaining what it is? But I'll do that shortly. The first law. Personally, my favorite law. I remember there was this physics book, Fundamentals of Physics, I think by Nelson and Parker. And I read it. It was a massive, thick, hardcover book. I was idle and interested. Fell in love with physics early. And I remember reading this first law. And for some reason, it stuck. The first law states that an object will remain in a state of rest or uniform motion in a straight line unless acted upon by an external force to do otherwise. A mouthful. Let me go it over again. An object will remain in a state of rest or uniform motion along a straight line unless acted upon by an external force to do otherwise. Simply put, any change in an object's motion, whether it be starting motion, stopping motion, changing direction, is a byproduct of an unbalanced force. Okay? Not just a force, an unbalanced force. If we have a 2 Newton force acting against a 2 Newton force, the forces cancel out and there is no resultant change in motion. However, if we have a 3 Newton acting against a 2 Newton force, there is a resultant force, an unbalanced force, and hence a change in motion. This is Newton's first law. Time for us to look at momentum. Now, remember that question that was posed? What happens if force becomes zero? If the force causing an object to move is totally removed? A question that Aristotle could not answer. If you hear that, it's a plane. I mean, this is Guyana. If you live in Georgetown, you hear them a lot. Don't panic. Nothing's wrong with your TV, and probably the plane is not flying over your house right now. It's just a plane. No biggie. Plane gone, I can continue. So, if the force that caused motion is removed, what tends to happen is that the object's momentum keeps it moving. It's why when you kick a ball, your foot only makes contact with the ball briefly, but the ball still moves. The ball's momentum carries it in the direction you want. Hopefully you kicked it in the direction you want. Just hopefully. Now, momentum is a product of mass and velocity. Momentum has a weird letter representing it. The letter is common or lowercase p. I really don't know why. I guess they were out of letters at that point in time and m was already taken by mass. So, hey, momentum, take p. Small p is equal to m times v. And all common, all lowercase. Lowercase p, lowercase m, lowercase v. Momentum is mass times velocity. And momentum can simply be defined as the property or what an object possesses that would keep it in motion even after the force that caused motion has been removed. Simple definition for momentum. Momentum, again, has its own principle. Just like you have the principle of moments, there is the principle of conservation of linear momentum. And I mentioned the principle of moments for a very specific reason. Please don't say the principle of moments is the same as the principle of conservation of linear momentum, for they are not. The principle of conservation of linear momentum simply states that the vector sum of momentum before two objects collide, or objects, you could have more than two, collide, is equal to the vector sum of momentum after they collide. All right? Momentum before collision is equal to momentum after collision, provided that kinetic energy is conserved. Now this condition creates two types of collisions. Elastic, which are collisions in which energy is conserved, or inelastic, collisions in which energy is not conserved or lost. Energy is primarily lost through sound and through deformation. When two objects collide, deformation can occur. Okay, so elastic collisions, energy conserved, none lost. Inelastic, sadly, energy is lost. So, to go it over again, momentum keeps an object in motion even after the force that caused motion has been removed. The principle of conservation of linear momentum states vector sum of momentum before a collision is equal to the vector sum of momentum after. And there are two types of collisions. Elastic, in which energy is conserved, and we can apply the principle of conservation of linear momentum to these, or inelastic, where energy is not conserved and we cannot apply the principle of conservation of linear momentum to these. This has been enough talking on my part. I hope you learned something. I hope you remember something from this very long revision session.
Da 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 da.
I hope you make your cheat sheets, share them with your friends, even ask your teachers for help if necessary. And I, Marvin Lee, will see you on the next episode of CSEC Physics. We have a lab to do. See you then.